Okay, everybody, welcome to our next lesson. Today's lesson is on translating graphs. So, two main learning goals are happening for today. First is to understand the effect of a translation on the equation for a graph, and we're going to focus on the basic graphs we talked about earlier. And then to actually draw the graph of a translation, and remember the word translation means a shift of one of the basic graphs based on its equation. Essentially, the prior knowledge that you want to have is knowing the basic graphs. First of all, it's important that you actually know each one of those by heart, so it makes it way easier to actually sketch a translation of them. And then making input-output tables is important based on an equation. So we're going to dive right in with an example. So here we have sketch the graph of y equals the square root of x plus 2. Now, you've probably at this point already gotten the idea, since we've done a lot of preparation for this, that this, and I'm just going to give it away, is a shift 2 units left of we usually call it the parent graph, y equals square root x, right? So we often call this, again, the parent, okay? But we're going to go into a little bit of some depth on why this works the way it does, I suppose. So what we can do is imagine, okay, that we call this, actually, I'm going to use the variable m here, y equals square root of m. Now, that is, of course, the basic structure of this function is the square root. That's what affects what the shape is going to look like. And if we were to actually make an input-output table with m and y, so again, just the basic graph, now notice that we cannot have anything, m can't be anything lower than 0, because we're working in real numbers, right? We're not going to worry about imaginaries at this point, right? So 0 is the lowest it could be, and the square root of 0 is just 0. And then the square root of 1, and I'm going to choose numbers that have nice square roots. So I'm going to do 1, 4, and 9 as my inputs, so I can get 2 and 3 as my outputs, okay? And since this is a function already defined to be the positive square root, we don't need to worry about the plus or minus business, actually. So if this was just to be that, then I could certainly just graph these 0, 0, 1, 1, 4, 2, and then 9, 3, and you can kind of see that, like we said, we don't go lower than 0, so it's almost like this graph has a starting point. Not all graphs do that, but this one particularly does. And you can also remember that this is essentially a sideways parabola, like cut in half, right? So there's my kind of shape for that original graph, or the parent graph. But if I've kind of set x plus 2 to be equal to m, right? So we've essentially set m equals x plus 2. Then we can alternatively see, if we solve that for x, that x equals m minus 2. And that's where the idea of why this goes the opposite direction than you may think, right? You see the plus 2, and it's tempting to think that this shifts to the right 2 units. But actually, when you allow x plus 2 to be equal to, in this case, we'll call it m, you can see that actually that x is equal to 2 less than whatever m was, right? So what I like to do actually here is just kind of make a table that extends back here, and actually my x values are going to be 2 less than whatever's here. So the number that's kind of behaving like 0 used to behave, and that's kind of how I think of this, is what behaves like what, is actually negative 2, because when I plug negative 2 in for x in the original one, that's what brings it to 0, because you have the plus 2 in there. So this is behaving like 0, my starting point. And then this minus 2 is negative 1, and then 2, and then 7. So instead, these inputs are the ones that make 0, 1, 2, and 3 as those outputs. So I'm going to do this. Negative 2 makes 0, negative 1 now makes 1, 2 now makes 4, and 7 now makes 9. In fact, you can see that all of the points on my original one have been shifted to the left by 2 units. So now I can sketch this out, and they're essentially, you could think of them almost as being like parallel, but some of the, it may not look like it, plus I didn't draw it all perfect, but that's essentially the idea and the concept behind what's going on here, okay? So you can think of how it relates to the parent, and if you make a table for the parent, you can then adjust whichever variable you need to, so that those are the new, in this case, inputs. But we can do the same thing to y if we want, to the outputs. Let's take a look at another example here. Okay, so here's another note before we get to our other example actually. As I said, this idea works the same for y too, only that would represent a vertical translation or shift. So the main point here is this. In general, if we have a function y equals f of x, then we often use h and k with the x and y here to represent these shifting numbers. Y plus k equals f of x plus h represents a translation, and it translates vertically k units in the direction opposite its sign, and then horizontally h units in direction opposite its sign. So it seems like a mouthful, but if you just remember, if you've added or subtracted to y, then you've shifted vertically. If you've added or subtracted to all the x's in the function, then you've shifted horizontally. And you just have to remember that the direction is opposite whatever the sign is of that number there. So let's go ahead and jump right into another example, okay? This is the same idea where if we wanted to, I could call this, we could call this n if we wanted to, and we could kind of realize, oh, okay, well, this is now my output I'm using a replacement variable for here. So I could make an input-output table for x and n first for the absolute value. And absolute value has all real numbers as its domain. So I'll put some negatives and 0 and some positives. And we know all it does is make it positive, right? So it just becomes those outputs. The only difference here is exactly what I said in the last one where, oh, well, we've set n to be equal to y minus 3, and therefore y is equal to n plus 3. So the actual y we want to match with each of these x's is actually going to be 3 more than those n's, not 3 less. So this becomes 5, 4, 3, and then 4, and then 5 again, okay? So again, that represents the fact, if we look here, because this is y minus 3, it's been shifted 3 units. It's tempting to say down, but it's actually been shifted 3 units up, right? So here's my inputs and outputs for my actual shifted function, right? So 0 makes 3, negative 1 and 1 both make 4, so I'll just do that. And then same here, negative 2 and 2 make 5. And we've got that familiar V shape of the absolute value graph. And again, it's just been shifted up 3 units. Okay, now, unless I've specifically asked you, it's totally okay for you to just sketch the graph in. You don't necessarily need to make the table for this like I have every time. This was just an illustration to essentially prove why it works the way it does for you. Okay, but the main thing for you guys to remember today is this general rule here that we wrote down. So with that being said, let's just jump right in and start doing a couple more examples here, and then we'll be able to end off for today. Let's look at another one that's based off of familiar one of these to us. And in fact, I don't think I'm going to need that much space, so I'm going to move my graph up here. So sketch the graph of, this is kind of complicated looking, x plus 5 all squared plus y minus 1 all squared equals 9. I just want you to remember, try to identify the parent, okay? So what I'm going to do here is look at the parent being x squared plus y squared equals, and I'll just say equals 9 is the parent, okay? And this is a circle, okay? That's something you kind of need to get the hang of recognizing, is look at the structure of the equation and knowing what shape it's going to be based on our basic graphs we learned. So this is a circle, the parent is a circle with center 0, 0, but the radius is 3, because don't forget the radius is the square root of this number on the other side of the equal sign. And since all we've done is shifted things here, right? Is the radius going to change? Nope. The only thing that's going to change is the location of the circle. So essentially we can move the center, and then just use the radius to actually draw out the new circle, right? So this is then, so I'm just going to say the new center. Well, let's look here. This is a shift left 5 units and a shift up 1 unit, right? So if my center was 0, 0, and I've gone left 5 and up 1, my new center is at negative 5, 1. And of course my radius is still 3 here. And so what I've got here is all the information that I need. So let's actually just look at my original circle. If I was to graph this, I would just look at the center, and then easiest thing to do is just go in the vertical and horizontal directions, whatever the radius is, in this case 3, and then you can kind of draw it in and fill the circle in. You don't really need to calculate more points. This can give you a good enough shape. But our only difference here is we've actually shifted this back 5 and up 1. So our circle is now located in a different place. And I can just go out 3 from that new center and get its new location. Okay? Another example, this is one that we have been familiar with actually recently. Sketch the graph of y equals x minus 2 cubed plus parentheses x minus 2. Now again, just have a hint in your head. If the y or the x has something added or subtracted with it, especially if it's in parentheses, you want to recognize, oh, that may have shifted the whole entire graph. Trying to get my camera focused here. That's a little bit better, but so let's just go ahead and identify what the parent is again. This one we looked at and studied in a recent lesson. The parent here, if you think of it, imagine the x minus 2 being something else. And I'm not using the m and n this time just because we're kind of familiar enough with what's going on and realizing what the shift is going to be. So you can see that these x's have been replaced with x minus 2, so it represents a shift to the right of 2, right? So I'm gonna write that. Shifted right 2. And you'll notice both x's, all x's involved in the original function, have been replaced with x minus 2. If only one of these x's was replaced with x minus 2 and the other one was just plain x again, that actually does not represent a shift anymore because you have to replace every single one of the variables in the formula with whatever it is to make sure the whole thing shifts, right? Otherwise, you could almost think of it as like some of it kind of shifts, but that's more complex than we're going to get to in this lesson. So let's take a look now. And if we wanted to, we could actually just make a table, to be honest with you. And I'm going to do it a little bit differently this time. I'm going to just say old, new. And we can just know that they have to shift right 2, which means I need to add 2 to my original x's. Now, if I just were to do something like, we know that all numbers are okay to put into this function. If I do those calculations, I'm gonna get a negative 10, a negative 2, a 0, a 2, and a 10. Again, just if you plug those numbers in. And what that's gonna give me for the old graph, and I suppose I should have color-coded this again, so let's just circle this with light blue, and we'll circle this one with dark blue, and that's what we'll do those graphs in. Is we're gonna get, I'm gonna plug these numbers in, and we're going to get a graph that looks kind of like x cubed, like we already talked about what this looks like, but like a stretched out version of x cubed. Okay, so this is what this graph looks like right here. And what's the new one going to look like? Well, remember, all we got to do is add 2, right? Because we know it shifted right 2, and you can just think about that m replacement that we did in our early examples. And these x's now have to be added by 2. So it's actually going to be 0, 1, 2, 3, 4 that make negative 10, negative 2, 0, 2, and 10, right? So these, for the parent, so when I say old, I guess I should say that's the parent, right? These are the inputs that make those outputs. But now these are the inputs that make those same exact outputs here, right? They have shifted up by 2. So all we need to do is really take this guy right here and realize that all these points are just shifting over 2 units. And then we can just sketch the graph right there with it. And again, you can almost see these graphs look like you can almost say the word parallel. They're not straight lines, so we wouldn't necessarily say parallel, but they don't intersect each other, right? Because we haven't affected the shape in any way except just shifting it. Yeah, there's another example to relate one of the graphs that we've recently seen that was kind of new to us, and take a look at how we can sketch a graph of a translation. There's only one other thing to look at today that I wanted to spend some time on with you guys, and that would be that this concept really relates well to solutions of equations too. So if we look at this equation right here, I want you to realize we could almost think an equation could have a parent as well. What I'm going to do is set the same thing. I'm going to let another variable, we'll call it m, and we'll let that equal x minus 3. So this looks kind of complicated and ugly, right? But you can almost see that it's quadratic in its structure. And if we replace this with m, then that becomes m squared plus 9m plus 14 equals 0. And you all know how to solve this now, right? This is quadratic, and I've made it on purpose factorable, so you don't have to use any ugly, quadratic formula right now or anything, because we're just kind of looking at the concept. This factors into m plus 7 and m plus 2, because 7 plus 2 is 9, and 7 times 2 is 14. And therefore m equals -7 or -2. The only thing here is we can't just call it done, because we're trying to solve this equation for x, and we allowed m to be the quantity x minus 3, right there. Those are equivalent to each other, right? So this and this are the same as each other, right? So if we know that m equals x minus 3, same as we did before, we know x equals m plus 3, right? So our actual solutions are going to be this plus 3, which is -4, and this plus 3 is +1. And notice something here. This is shifted up by 3. So just like the graph's shifting up by 3, right? Whether it's the x or the y, or however much, shifting left, right, up, down, depending on what. A solution to an equation will follow that shift as well, right? So you can think of the parent equation like this, and the solutions to this equation will simply be 3 more than this guy's solutions. So that same concept applies to equations. Well, that is it for our lesson today. And again, happy math, and we'll see you guys later.